Hi folks, and welcome back to Physics with Captain Rod. This is video 2 on a two-part series here on numerical integration. So I've left my work from the previous video here, and again, just a quick reminder, the first video was about how to find the area bound between or under the curve y equals x squared from x equals 2 to x equals 6. So we've got a lower bound that I call a equal to 2, upper bound b is equal to 6. I've got my delta x here. In my previous video I discussed where these formulas are coming from, and again the big one I want to discuss here is the x sub I. So the x sub I is the x value needed to calculate the length of each rectangle where the rectangle is centered on the function value here. So for example, this would be what I would be calling x1, would be actually this distance from here to here, and again it's right to that spot, the center of that rectangle. X2 measures to the center of the second rectangle, and so forth. And again, these rectangles are centered to give us a pretty good estimate for the area under the curve. Now in Excel, Excel is just a wonderful program for doing this type of numerical work here. So what I'm going to do is I'm going to start by just putting in my data here. So in this cell I'm going to put A, and then I'm going to move over to give the value 2. I'm going to put it B here. Here's my upper bound, and then I'm going to move over a cell here and put 6. Now, another variable of interest or that we have to choose here is the number of rectangles. So I'm going to put that here, and for right now I'm going to call that n. And I'm just going to put a value here. For now we'll say 10 rectangles. I find that I can use 10 rectangles here and get pretty good results with most problems. As a rule of thumb, accuracy tends to go up when you use more rectangles, but there is a limit. Eventually what can happen is your rounding error can start getting bigger and bigger and bigger if you use too big a value of n. And again, that's things you learn about in a more, I'll just say a more advanced numerical course. For now, 10 rectangles works pretty well for most of these problems. The very first thing I'm going to calculate now is the delta x here. So I'm going to come right down here and type in, I usually call it something like del x. Rather than actually typing in numerical values, what I'm going to do is I'm going to program Excel here with a little formula for calculating it. And the way you do that in Excel is you hit equals. And when you hit equals in Excel, what it does is you're telling Excel there is a formula coming, and that formula is going to be this. I'm going to open a parenthesis, and I'm going to click here. That's my upper bound. Subtract my lower bound. Close my parenthesis. And then I need to divide by the number of rectangles. You'll notice I'm building my formula by clicking on cell locations rather than typing in numerical values. And Excel, when you hit enter there, Excel calculates it at 0.4. Now let me talk about why I clicked on cell locations rather than typing numbers in. If I go back here now and I want to change my, say my lower bound not from 6 to say, I don't know, 9. You'll notice that when I change any of that data, Excel will automatically update all of your calculations. That's a really, really nice feature. All right. We can use that lots of different ways for studying lots of different things. I'm going to go back now and change that back to a 6 to match my problem. All right. Next, now I'm going to start having Excel calculate this stuff, starting with the i's. So I'm just going to build a column here, and I'm going to call it I. I'm going to come down here and type in 1, 2, 3. Okay, Excel's really good at recognizing patterns. If you click and highlight it, 1, 2, 3, and I come down here and grab this lower corner, Excel recognizes the pattern and will fill all of them out for you, which is nice. Now if you had 10 of them, no big deal, but if you were going to use I equals 1,000, you don't want to have to type all that in. All right. Next thing now, I'm looking right here. Now I want Excel to calculate these x sub i's for me. So I'm going to come up here and I'm going to actually label them x sub I. I'm going to come down here and I'm going to give Excel a formula. So I'm going to hit equals. Now I'm just following my own equation here. This 2 was the lower bound. So I'm going to come up here and click on the lower bound. And now I'm just going to type in exactly what I've got in that formula. Plus I times delta x. I'm looking right here. I times delta x. Rather than typing a 1, though, I'm going to click on that cell location where I is stored, times delta x. And then remember, we have to subtract off half of delta x. And what that does is it centers the rectangle. So minus 0.5 times delta x. So there's a formula that should calculate my x value. If it gets it right, the first one should be 2 plus half of delta x. I think that should be 2.2. And we go, yay. All right, now in Excel, when you grab the formula and you drag these, if you click on the cell where the formula is and you drag the lower corner down, what it will do is it will fill all of this out. Now, I'm purposefully not hitting enter yet. I want to think about what that upper bound should be, that value for x, if we did this right. The upper bound in this problem is 6. But remember, we're centering the rectangles. And since the delta x is 0.4, 5.8 would be the correct x value for the very last one. So I'm going to go ahead and release this, let it calculate it, and we'll discuss the results some more. Oh, so we look at this and we go, well, that's not 5.8 on the very bottom, right? And there seems to be a whole bunch of problems. All right, Excel is really cool about telling you when it's got a problem. It's really cool about not only telling you when there's a problem, but it's cool about telling you what the problem is. If you see a value you don't believe in, like this one right here, and you click on it, Excel tells you what it used to calculate it. You'll notice it used this 10, which is good, but you'll notice it used this thing here and this thing here. These are not values it was supposed to use. Well, here's the mystery to what happened. When you scroll down in Excel, any cell that you reference scrolls down with it. This stuff that was referenced up here, we don't want that to scroll. We want that to be locked down. So I'm going to go back to the original formula. And I've double-clicked on it. And it's nice that it even color codes this for you. This A10 here that's orange, we want that one to scroll down. We want I to go 1, 2, 3, 4, 5, etc. But this B2, we don't want that to move. We want that one to be locked down. So the way you fix that is you go right behind it, and I clicked on it. And on a PC, if you hit F4, you'll see these dollar signs appear around the B and the 2. I call this double dollaring. When you double dollar something in Excel, it effectively puts a nail through it. It nails it down and it will not let it scroll in any direction. I'm not sure what the command is on a Mac or an Apple computer. If somebody's looking at this and you're using a Mac, you're kind of on your own to find that. I don't know what it is. But on a PC, F4 will double dollar these. All right. Now, as I look at this purple B5 has to be double dollared. And there's another one right there. So F4, F4, double dollar, those are now locked down. Click, reapply the formula by dragging. If this is correct, the last one should be 5.8. And we go, yay. Okay, next part of the formula here. All right, f of x sub I. So I'm going to come over here. F of x sub I. Now that's just a label. I'm not calculating anything. Here I'm going to click, give it a formula, and that's going to equal, in this example, x sub I squared. I like to use the caret button as a generic power button in Excel. You can get a square root with it, a cube power, any power you want. And of course, if I square this, 4.84, grab, drag. There's all of them. Next thing in Excel, okay, we need the a sub i's here, area of the ith rectangle. So a sub I, and that again, that's just a label. Move down here, hit equals to tell Excel you've got a formula coming, and it's equal to the function value times the delta x. Now, anything that's referenced up here, we got to lock that down. We do not want that one to scroll, so we F4 that animal. grab, drag, and Excel calculates all of them for you. All right. Now, well, in the end, what we got to do, right? These numerical values represent the area of the individual rectangles. We have to add them all up. I'm just going to maybe come up top here and put a total. Now that's just a label. I'm going to move over to the right now. Now why right? I don't know. You can move down, left, any direction you want. And now I'm going to give it a I'm going to give it a formula. Equals. Now what we got to do is add these up. Excel has just umpteen built-in functions, which are really nice. One of them is a summation function, so I'm going to put equals sum. Oops. And there we go. Sum. And then parenthesis. And all you got to do is click, drag, hit enter, 69.28. Now, just as kind of a check of accuracy here, I got to kind of move my computer around to do this because I got it in a different mode here. I'm going to put it in tablet mode here, and I'm going to check that value against the numerical calculation for that area. Give me a moment. All right, and I'm going to have to kind of do this right through the middle of the work here. It's not too tough to show in a first semester calculus class that the area bound under that curve, y equals x squared from 2 to 4, is going to equal, oops, the integral to, oh, I'm sorry, I said 4, I meant 6. Integral 2 to 6, x squared dx, which is going to be x to the third over 3, evaluated from 2 to 6. And what I'm going to do here is I'm going to take a moment, let one of my helpers calculate a value for me. Six cubed over 3 minus 2 cubed over 3, hit equals, please. And one of my helpers gets 69.33. Now, you'll notice that you got to get the 3 sig figs here to even see a difference. Error-wise, this is a very small percent error. In fact, I'm going to take a moment and actually estimate the percent error here. Would somebody please give me? Let's see. I need to erase some stuff here. And I'm just going to carry 2 sig figs for this error estimate. But the error here is going to be this value, 69.33, minus the value I got on the right, 69.28, divided by the accepted value, 69.33 times 100. Would somebody please calculate that difference for me? Approximately 0.07%. And I'd like to point out that's not 7%, that's 0.07%. That's already been multiplied by 100. You'll notice in this example we got, less than 0.1% error using just 10 rectangles. Now, other curves can give you much more trouble, especially if you're approaching things like asymptotes. You have to be more careful. What I do when I'm approaching asymptotes is I typically will break it up into quite a few more rectangles and things like that. But I think this video is good for just giving the basic idea of how this works. So I think that's probably enough for this video on numerical integration. I hope it gives you, at least a reasonable feel for how to set up a set of calculations, I'll say, for calculating an area under a curve numerically, and how to use Excel to do that, do the brunt work for you. So, everybody have a great day. 14 minutes.